this is interesting because, all right, so yesterday I introduced this whole geometric series, and let's just sort of refresh our memory. For a geometric series, what three pieces of information do you need? First term.
Common ratio.
Okay, so we need our first term, we need our common ratio, and we need the number of terms. And we get this lovely little, formula that the sum of the first n terms of a geometric series is your first term times 1 minus your common ratio to the number of terms all over 1 minus the common ratio. And the intent of the problems I gave you yesterday was practice this enough so you get comfortable with the formula. So let's pick up. That's where we stopped. Now we're going to pick up there. First, does everybody recognize that this is a geometric series? So if it's a geometric series, what's the common ratio? Is everybody okay that our common ratio is 1/2? All right. So here's our geometric series, and we know that our common ratio is 1/2. What's our first term? 1/2. Okay, so our first term is 1/2. Okay. But the difference about this question and all that I did yesterday is, see that I have a dot, dot, dot? See, normally when I give a dot, 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 I put a term here where it ends. This one doesn't end, right? Right? So we just keep adding numbers, right? You just keep adding numbers, And you'd think if you just keep adding numbers, they keep getting bigger and bigger and bigger, right? And so you wouldn't be able to get an answer, right? Isn't that what you think? That's what I would think. But in certain geometric series, that's not the case. In fact, this, if I add all these up, like the next one would be 1/64, 1/128. As you keep adding those up, my claim is this ends up being a very nice number, right? Now, before we do it algebraically, I get excited about it. I saw a picture of this once, and I was like, this is really cool. What we're going to do is we're going to describe this situation with a picture. Ready? So I'm going to start off with a shape that I know everybody knows. I'm going to start off with a square of side length 1. So what's the area of that square? Everybody okay? The area, this is 1. Really tough question, right? All right. So are we okay that this total area is equal to 1? That's a big part of this. All right, well, I'm going to draw a line exactly down the middle. And what's the area of this part? Are we okay that the area of this part's 1/2? All right. And over here, I'm going to draw a line down the middle. What's the area of this part? Okay, the area of this part's 1/4? All right. And over here, I'm going to draw a line down the middle. What's the area of this part? And over here, I'm going to draw a line down the middle. What's the area of this part? And over here, I'm going to draw a line down the middle. Guess what the area of this part's going to be? 1/32. Do you see the pattern I'm doing? Does everybody see that I can keep drawing a line down the middle, right? Keep drawing a line down the middle, right? See how these numbers are up here? So if you add up all of these, 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1/28, if you add them all up, what's this total area equal? 1. So guess what this whole series equals? 1. I like that. Do y'all see how that worked? Now, just so you know, this is the only infinite geometric series I can draw a picture with. All the other ones, sorry, we're stuck, right? But I'm trying to give you an argument of why, if you add all the little parts, it equals 1. Can you see why if you add all the little parts, it equals 1? Because you add all the little parts, you're basically filling in the area of a square, right? So that's the picture part. Now let's see how the algebra looks. Okay, ready? And actually, before we see how the algebra looks, I want to deal with what happens when you raise something to a power. So in particular, I want to think of, so we're going to pause just for a second. And so I want to think about, well, what's 1/2? If I raise 1/2 to the 10th, can we see that this is going to give me 1 over, and 1 to the 10th is 1, 2 to the 10th is 10^24. Do you see that 1/2 to the 10th is a really small number? Okay, so can we agree that 1/2 raised to the 10th power is going to be a pretty small number? Can we agree that 1/2 to the 100th is going to be 1 on top of a huge number? And so 1/2 raised to the 100th is going to be really small, right? In fact, I think that's going to be so small, if you type that in your calculator, the calculator will say, I give up 0. It's going to be so small the calculator can't even acknowledge it's different than 0, right? And that's at 100, right? If this is 1,000 or 1,000,000, I mean, can we agree that when you take a fraction and you raise it to a big power, it basically goes to 0? All right, so given that information, let's use our formula. This is a geometric series. And since this is a geometric series, we can use our formula. So when we use our formula, it's going to be, I needed more room. So you already told me that my common ratio was 1/2 and my first term was 1/2. So let's see. We're going to sum up this series. And you told me my first term was 1/2, so I'm going to put a 1/2 here. Then it's going to be 1 minus 1/2 over 1 minus 1/2, right? Your first term, 1 minus your common ratio. How many terms do we have for an infinite geometric series? Say it? Infinite. A lot, right? Can we agree that like this represents the number of terms and we basically have all of them? And so this is raised to the infinite power. And then it's over this. Now you'd think that that makes your life really hard, makes your life more complicated, because look at all these fractions. And technically I'm not supposed to put an infinity for a power, but I want something to get the idea. But what I want you to think about is, what is this really? What's the value of 1/2 raised to a giant power? 0. That's what we talked about over here, isn't it? If you take 1/2 and you raise it to a big power, it just basically goes away, doesn't it? Well, wait a minute. So if this just goes away, what are we left with? What's left on top? 1/2. And what's 1 minus 1/2 on the bottom? 1/2. And what's 1/2 over 1/2? What's 1/2 over 1/2? 1. Oh, good. That's what we found out over here, wasn't it? So mathematically, right? So here I did with a picture, and this is the only one I can do with a picture. So when I start doing the other infinite geometric series, to ask what's the picture look like, I don't know, right? But for this one, and mathematically, you see how we ended up with 1. Now, here's the cool part. When you have an infinite geometric series, it's a geometric series, so it's going to, this is how you sum up a geometric series. But for an infinite geometric series, and the notation for it is this, they put an S and they put a little infinity, sum of an infinite geometric series. And when they look at it, they say, this thing is going to go away. Because if your ratio, right, that's what happened here, right? Remember how we had our ratio raised to the infinite power? So our ratio raised to the infinite power, it goes away. So when this thing goes away, the only thing, what I have left on top is the first term, and what I have left on the bottom is 1 minus the common ratio. So when you want to sum up an infinite geometric series, that formula, I think, is way easier than this formula. So what information do you need to sum up an infinite geometric series? How many pieces of information do you need? 2, right? You just need the first term and the common ratio. Does that make sense? So, for example, let's see. let's say I do 3 minus 9 over 4 plus 27 over 16 minus 81 over 64, dot, dot, dot. Can you recognize this as an infinite geometric series? Well, we know it's infinite because of the dot, 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 right? Can we recognize it's a geometric series? So if it's a geometric series, what's my common ratio? Okay. How'd you get that? Did you look at the first two or the second two?
First two.
Oh, you're better than me. I looked at the second two. See, when I look at, you can usually get any two, right? They've got to be right next to each other. And your common ratio is, what did you multiply to get here? And if I think about it, well, I multiplied the bottom by 4 and the top by 3. And since the sign changed, it better be a negative. Is everybody okay? That's your common ratio? All right? So if I know my common ratio, it turns to sum up an infinite geometric series, I just need to know the first term in the common ratio. Well, what's my first term? That was tough, wasn't it? That was really tough, right? So our first term is a 3, and our common ratio is negative 3/4, so I'm going to do 1 minus negative 3/4, and then I'll work it out. So let's see. This is 3 over, well, that's going to cancel, and 1 is the same thing as 4 over 4 plus 3 over 4. So that's going to give me 7 over 4. And the way you do it with these layered fractions is you want to think about this as this is 3 divided by 7/4, which is the same thing as 3 times 4/7. So you get 12 over 7. So 2 questions. Did that kind of make sense? You see how we use the formula? Second question, is it easier to use this formula than this formula? A lot easier, isn't it? Because what was the pain about this formula? You got some common ratio with this a fraction. You got to raise it to a power, right? And it's just really ugly. But when you're dealing with an infinite geometric series, right? You don't have to worry about that at all. You just put a number here and a number here. All right? Is everybody okay with that? So, actually, you like infinite geometric series more than regular ones. Because I think it's just simpler. But there's a warning. I can tell you the warning. But to be honest, it has more a lasting effect if you experience the warning, right? So we're going to experience the warning. So what I'm going to write an infinite geometric series. My infinite geometric series is going to be 2 plus 6 plus 18 plus 54 plus dot, dot, dot. Okay, we see that this is an infinite geometric series. Right? Is everybody okay? It's an infinite geometric series because we know it's a geometric series, right? What's my common ratio? 3, right? Anytime I say geometric series, you need to be able to tell me what the common ratio is. So, geometric series, we know that our common ratio is 3. We know that our first term is 2, right? So if I'm going to sum up an infinite geometric series, I go, well, hey, no problem. I'm just going to use my handy-dandy formula, right? And my handy-dandy formula says, well, let's see. Handy-dandy formula says, well, if I'm going to sum up an infinite geometric series, I need my first term, which is a 2. And then it's 1 minus the common ratio, which is 1 over 3, right? Because we're just blindly using a formula, right? That's a dangerous thing, by the way, right? You just never blindly use a formula. You know, I go through this whole thing, I end up with 2, and then over negative 2, and I get negative 1. Does that answer make sense? Thank you. It doesn't make sense, right? I would be disturbed if I give you a question like this on your test, right? And you just say, okay, my answer is negative 1 and move on, right? I want something to go off in your head and you say, there is no way you can add up a bunch of positive numbers and get a negative number, right? Can everybody see that? Like, would you deserve to miss the question if you use the formula and got -1 off of this? Because there's no way, right? So here's the warning. When you sum up an infinite geometric series, you have to make sure that your common ratio is small, right? The reason you can sum up an infinite geometric series is the terms keep getting smaller and smaller. And the only way that happens is if your common ratio is less than 1. See, if your common ratio is bigger than 1, like this, see how the numbers keep getting bigger? And if the numbers keep getting bigger, then you're not going to get an answer. This actually has a special name, right? Whenever you have an infinite geometric series where the numbers just keep getting bigger, this is an example of something, it's called divergent. And so when you have an infinite geometric series where your common ratio is big, right, where the numbers keep getting bigger, you're going to get a divergent series, meaning you're not going to get an answer. It blows up. It goes off to infinity. All right, so let's compare that. So divergent means you don't get an answer. What's the word that we're going to use that says you do get an answer? What's the opposite of divergent? Yeah, good job. Convergent. So if it's divergent, you don't get an answer. And like the previous two examples, those were examples of things that were convergent. Does that make sense? Is everybody okay with the terminology? Yes.
So would you just say that the sum of a divergent is just infinity?
Or you say it's divergent. Okay. Because honestly, you don't know if this one we know is going to positive infinity. But when your common ratio is negative, what ends up happening is because it alternates, like you get giant negative number followed by even bigger positive number followed by even bigger negative number. And so it's not getting close to positive or negative infinity. It's actually going to both at the same time. So rather than say that, we just say the word divergent because just think divergent means you don't know where it's going. Convergent, like if you think converge to something, you know where it's going. Does that make sense? Well, and actually, I need to be a little more precise here. It's not just that your common ratio has to be less than 1. Your common ratio has to be between -1 and 1. Like our common ratio has to be close to 0. Like it's okay, like it's your common ratio, like common ratio of 2/3 is fine, common ratio of -4/5 is fine, but a common ratio of -10 is going to be divergent because it's going all over the place. Okay? And I want to make sure you have a picture. This is the way I write it, because the way I write it is it kind of describes exactly what it is. This says your common ratio is in between -1 and 1. See how it's written that way? Like it's written where they're saying, okay, so your ratio's got to be somewhere in between -1 and 1. It's describing this picture. You've got -1, you've got 1, and your common ratio has to be somewhere in here. If your common ratio is not in here, then it's divergent. So far, so good? But some textbooks, and in particular Know or Math, they don't write it this way. What they do is instead of saying R is in between -1 and 1, Know or Math describes this as, they say the absolute value of R is less than 1. And believe it or not, this is actually describing the same picture. So it's like if you take your common ratio, you take the absolute value of it, you want to make sure that that's less than 1. That guarantees that you're in this range. All right, are we okay with this? All right, so as far as using your formula goes, it's like if I give you the first term, I give you the common ratio, it's easy, you just plug it in. Well, just like other situations, like those are the easy questions. The harder questions, which really aren't as bad, what if I start giving you different information? Like, let's say I tell you that the first term is 96, and the sum, and the infinite sum is 64, and I want to know, what's my common ratio? Does everybody see how we could use this formula to help us figure out what our common ratio is? Because, when you get a formula, you have to use it. And how you use a formula, the way you, the forward way to use a formula is I tell you the first term and I tell you the common ratio, you plug it in and it tells you the sum. But the backwards way is, I just give you different pieces of information. All right, if I give you the infinite sum and I give you the first term, do you have enough information to figure out your common ratio? Because you just plug in what they tell you. If they tell you the sum is 64, I'm going to put a 64 on this side. If I tell you the first term is 96, I put a 96 on this side, and then I put a 1 minus r. Do I have enough information so that I could solve for r? I've just got an equation. Now, as far as solving this equation, I could just say solve it, and you'd get it, right? You could look at this and say put this over 1. You can cross multiply and solve for 1 and solve for r. But I'd like to show you my trick. I may have already done it, but I want to show it again, right? So my trick for this is anytime you have a number equal a fraction and the variable on the bottom, I've got a real technical term for this. What you can do is if you have a variable on the bottom and a number here, I call it that swappy thing. You can take this, put it here, and take this and put it here. And so I end up with 1 minus r is equal to 96 over 64. Now, honestly, I would prefer that you don't accept my word for this, right? Because I don't want you to accept anything a teacher says, right? Particularly in a math class. So there's got to be a reason. So, if you don't accept my word, which I don't want you to, right, that means we're going to have to cross multiply. So think of this over 1, and so this times this is going to give me 64 times 1 minus r is equal to 96. Then I'll divide both sides by 64, and so end up with 1 minus r is equal to 96 over 64, right? Oh wait, that's what I got here, isn't it? So it's just something that shows up frequently in math classes where you have a variable in the bottom, and what you can do is swap it with over here. Right? Oh, now to actually finish this, let's see, 96 over 64, 32 goes to both of those. And so this is going to give me 1 minus r is equal to 32 goes into this 3 times, goes into this 2 times, so I get 3 over 2. When I subtract 1 from both sides, I get negative r is equal to 1/2, or r is equal to negative 1/2. Does that make sense? All right, and the last thing I need to talk about, right, before we start working, because I actually want most of today to be spent on practicing this stuff. So your homework, what you're doing in class, I want you to finish the Knower math assignment. So that's 8 questions, because you've already done 1 through 7, so now you can do 8 through 15. And the 8 through 15 are all about this infinite geometric series. But I've also got a worksheet. And in this worksheet, there's some notation, and this is notation I'll actually talk about next week. It's called summation notation. And here's the important part of it. It looks this funny looking E, right? If you know anything about the Greek alphabet, it's the Greek letter sigma, but most people look at it and they think it's a funny looking E. And there's this stuff over here, like n equals 1 to infinity. I don't really care about that. What I do care about is what's over here. Like what's over here, let's say I tell you this is 3 and 4/5 to the n minus 1. Right? When you see this off to the side of, because they're asking you to, this actually, believe it or not, this represents an infinite geometric series. This part tells us the infinite part. And to do an infinite geometric series, you need to know your first term and your common ratio. Well, this is your first term, and this is your common ratio. And my claim is, you kind of already know this, because if you look at this, doesn't this look similar to the explicit formula? Doesn't this look really close to the explicit formula of a geometric sequence? And in your explicit formula, this represents the first term and this represents the common ratio? All right, that's not a coincidence, that's what happens here. All right, so let me hit